Welcome everyone, and thank you for joining us today. My name is Marcus Weber, and I will be the moderator for today's webinar. I am the Technology and Execution Council Chair in Fluor's Business Transformation and Innovation team. We focus on new and innovative ideas, never losing sight of the critical thinking and analysis that comes from our global team of expert engineers and designers. Our people are at the core of our success, and this webinar series is an opportunity to showcase specific expertise or to talk about new trends or code changes. In today's technical presentation will be a discussion about data-minded decision-making. A critical issue many businesses face is the ability to effectively predict performance and trajectory based on past data and plans. This presentation will overview tools and methodology to accomplish these predictions and provide guidance to apply them to your leading and lagging indicators. Our speaker today is Steve Prevette. Steve is a 25-year Fluor employee and American Society for Quality Fellow. He has supported 8 Fluor projects with analysis of their performance data, leading to success at application and presentation of the performance data. Steve helped Schumacher adopt these methods for their HSE trending and analysis. He also teaches data applications for Southern Illinois University at Carbondale remotely and has been published by multiple professional societies on the subject of statistical trending. His most recent presentation was Human Performance, Root Cause, and Trending Virtual Conference, which is the basis for this presentation. In his spare time, Steve and his wife Jenny enjoy scale model railroading. He is most proud of his N-scale model of the Burnt Hills and Big Flats Railroad. In fact, Steve gave a standing room only seminar at the Model Railroad Association event on the topic of statistics on model railroading for how to simulate traffic control.
Thank you for that introduction, Marcus. I appreciate everybody who's attending and the opportunity to share some information with you. Now, we are seeing at Fluor Corporation a push for being data-centric. There's a few slides from our internal website called One Fluor that has lots of topics on it. And we're especially using it at the upper levels in terms of project management. For those familiar with what an S-curve is, instead of saying this project is going to take 1.5 years, we say, well, there's an 85% chance that this will complete in 1 3/4 years or less. So we can put in some safety contingency plannings. And we actually are predicting what is the range of the budget, what is the range of the time it will take to do the project. And that helps a lot to understand the synergy between our experience with projects and what our data is telling us. Now, that's great at the very high level, but today we're going to talk more at the workplace level, at the line management level. What can we do with our data to be data-centric and understand our predictions and their uncertainties? So I want to predict the future. I can use, indeed, my past data to predict the future. We may need to understand what is our plans. Do we actually plan to change from the past? How do we know we need to change? A fine person named Dr. Russ Akoff, who I follow, did point out, well, it's one thing to predict the future. It's another thing to realize I don't want to live with a predicted future. How do I change it? So how do we know? And as we're proceeding with our work, be it maintenance, safety, project management, how do I know when my prediction is no longer valid? Now, as children or your children or your grandchildren get to learn a lot about this at Sesame Street. And there's a great song there. I won't try to sing it for you, but one of these things is not like the other. So we have this graphic from Sesame Street there where obviously I can see one bowl of birdseed, and of course this is from Big Bird's perspective, is much bigger than the others. I can see that. It's very straightforward. However, as I collect my data and try to put it into tables or moving average charts, I may not be able to recognize one of the birdseed bowls is bigger than the other. Now, this is an old problem. Now, we talked about in the introduction about we're bringing you new solutions. Well, I am going to talk about coming up on a 100-year-old solution. Now, my first person I'll talk about is William Gossett, and I wish I had his job description. The head experimental brewer of Guinness. Just went to an Irish restaurant last night and had a fine Guinness stout. So thanks to William Gossett, they perfected Guinness stout. You may or may not agree with me on that, but the point being is that he measured like the temperature they brewed at, the amount of hops put in. For those who are beer and ale lovers, you know all about this. But as he analyzed the data, there was a lot of uncertainty and random variation there. So he did determine, and for those who suffered through Stats 101, you are maybe remember the phrase the student T distribution and hypothesis test, where this was able to look at prediction intervals. Now, in 1930, Dr. Walter Schuhart, working for Bell Telephone Labs, also observed variation in product, in this case, telephones, which in that days, they had a rotary dial. They were black. There was like two sets, a desktop and a wall mount. Not very exciting, but they were supposed to all be workable, that they were to actually do the tasks they're supposed to do, but some of the things were a little out. Some of the products weren't like the others. So he developed statistical process control, published several books in the 30s that became the basis for what we now know today as statistical process control, as picked up by Dr. Deming and others, and the Japanese, with the recognition that data contains signal and noise. And how do I tell when I get a result that isn't like the others, that if this was just random noise, or if I have a signal and I need to pay attention to, well, what changed? And we'll talk about the what changed question is important if something really changed versus, well, this is the best the process is capable of doing, such as something called Dr. Deming's red bead experiment. You can Google that if you're interested, which is a stable process, very predictable, but not meeting our goals. And unfortunately, as we get into big data, more and more people are able to sling charts and accumulate large amounts of data. And oddly enough, this little slide was on a internet website saying this is a way to do metrics. Now, what we see here is a quarter last year compared to a quarter this year, one bar at 32%, 22%, one bar at 23%. For some reason, this stoplight, which is a good way to show information, is yellow. We don't know why. And we have this long write-up. I won't read it all, but, the turnover rate for the first quarter, Q1 of FY04, was 1% more than first quarter last fiscal year, but the total number of employees increased by 4%, 1,289 employees on July the 1st, 2002, 1,340 employees on July 1, 2003. Take a deep breath. My word, that's a lot of information, but what does it mean? Is a 1% change in the turnover rate really something I've got to understand? Maybe the turnover rate's too high. I suppose if I'm losing a quarter of my employees, that probably is too high. But from what I can tell, it sounds pretty darn stable. What do we learn from this? And that's kind of the question. This is a very tough, although simple, presentation of the data. So here's another standard presentation. If we go back to the theme of safety to try to, ground this with something everybody's pretty important, very important to everybody. I don't want to go home hurt. I don't want my friends and coworkers to go home hurt. So I want to minimize injuries. I don't want those rotator cuff injuries. So here's a typical bar chart you'll find on a bulletin board. Got a couple years of monthly data, and every bar is kind of different from the others. And oh my word, in February, the fourth bar from the end, such a great decrease from July 04 to January 05. This is wonderful, terrific, but alas, we lost all those improvements in March. What do we do? Well, I can throw on the 12-month moving average, very popular, especially in injury statistics. And now I learn, wait a minute, I'm not getting worse, I'm getting better. If I smooth out the data over a 12-month interval, and of course, we see that a lot on today's COVID charts, trying to understand what that's telling us. I see a pretty decreasing trend from the the summer 2004 to present, things are getting better. Well, this doesn't make much sense. So we'll try another approach. The red, yellow, green system, which I kind of alluded to. So yeah, we'll say anything less than a 5 is green. Oh yes, February was great. We got to figure out what happened in March 2005 because we set a threshold at 10, and oh my word, that's above it, and May's almost there too. What do we do? Well, there's another approach to this. So we're not just whipsawing after monthly numbers. We can do this statistical analysis that Dr. Schuhart alluded to, and I showed you an example of in the safety topic. We can plot our injuries per month, or be it our cycle time per month, or our number of corrective maintenances completed per month, or number of tasks completed, quality defects. I can plot a time series. Dr. Deming did say, it's so simple, just plot the dots. So we've plotted the dots. Now, to give some context, I throw in an average line, the black line in the center. Now, of course, an amazing lesson of this is about half the data is above average, half the data is below average. Yes, we all have children who are above to average students, of course. Well, sometimes the average line will tell us kind of the average. Yeah. However, it doesn't give me my extremes. It doesn't allow me to measure risk. So what for risk in determining if one of these things is not like the other, Dr. Schuhart came up with, let's set our limits at 3 standard deviations from the average. Somewhat similar to your smoke detector. It doesn't go off on the average amount of particulate in the air. It doesn't go off on the average amount of carbon monoxide in the air. There's some threshold above that average where below that threshold is likely the ongoing process in your house that puts particulate or carbon monoxide in the air, and above that threshold is unusual and probably you have a fire. And that's what we have here on our red upper line. If we were to have more than 21 injuries a month on this chart, then something's changed. And also, at the lower level, we want to detect, are we getting better? So I also throw my green lower control limit on that says, well, if I actually had 0 of these, it would be very unusual. Now, is 11 injuries a month averaging between 1 and 21 a good place to be? Well, now comes the talk of context. Now, if these are mosquito bites with very little effect, perhaps this is an annoyance and acceptable. Whereas if this is rotator cuff injuries, it's way too much of a penalty to people, a penalty to our process and our productivity. We've got to do something about it. So at least I can go in here and say this data, which is the same charts as the previous slides charts, are stable and predictable. I can predict the future that is somewhere between 1 and 21, averaging about 11. So now I have a prediction. So how do I know when something changes? Well, Dr. Schuhart did propose the 1 point outside of 3 standard deviations, and in certain documents, one that's out there is Institute of Nuclear Power Operations 07007, which happens to contain a trending plan I wrote. We also set lower level limits. So a big shift in a short period of time is detectable, and a subtle shift in a long period of time is also detectable. So a rule I do use is 7 points in a row, the same side of the average as a trend. I will admit to you, if you read Dr. Don Wheeler's books, he goes for 8. And if you have Mini-TAF software, they tend to go for 9. There's some subtle differences there and reasons. I like to go 7 because it's more conservative, especially when I'm doing safety or quality work. I do want to fail on a little bit more on the side of conservatism. So I also have 2 standard deviations as a threshold, 2/3 of the way of the control limit. If I get 2 out of 3 points in a row, I'll signal that as a trend, or 4 out of 5 at 1 standard deviation, or even the very long-term one of 10 out of 11 points. So you notice this curve, big shift, short period of time. It's a trend. Subtle shift, long period of time, it's a trend, and I have some intermediate rules for that. So I now can see one of these things is not like the other. And in fact, during the human performance root cause and trending, and I was their T guy, the trending guy, we did an exercise with the audience. Everybody was asked to pick a random number between 1 and 10. And as the talk went on, we accumulated data, and I plopped this into a control chart of sorts. It's not a time series, but we kind of accumulated a histogram with control limits, and noticed that the number 7 came up quite often. Hardly anybody chose the number 1, but a lot of people chose 7, which led to a very interesting discussion. It was some people's favorite player number in a sport, or at least in many cultures, we find that 7 is considered a lucky number. So there was a disproportionate amount of people who, when asked to choose a random number, actually chose the number 7, which wasn't terribly random. And we were able to tell that from the statistical test. So now if I'm applying this to work, and these are some of the articles that have been written over the years, charting safety performance and professional safety for, at the time, ASSE, now they're ASSP. Actually, Schlumberger read that article. They're, very important oil company in Houston, and they invited me for a week there to show them how to do this methodology, and they actually programmed it up and use it to today. Also for American Society for Quality, where I am a fellow of the Society, I've published several articles there with this, and they've been picked up by other papers and books. The basic concept is, let's use red, yellow, and green instead of as arbitrary thresholds as something that explains the process to us. So if I have that adverse trend, oh my word, I've blown the upper control limit in rotator cuff injuries, we will color it red, and we indeed need to understand what happened. Oh, the equipment broke, and the new equipment isn't very ergonomically correct for people to use, so let's fix the equipment. Of course, the bottom row is the good news, which is actually have an improving trend. What can I learn from it? Phil Monroe, who's on this, and myself, we're doing something called Dr. Deming's red bead experiment. And in that, people simulate making a product, a white bead product, but there's red beads that come up and they're defective. Well, at one cold, dry morning, Phil dipped in the paddle and we pulled out all white beads and went, well, that's below the lower control limit. That can't happen. We even tried it another time, and it happened again. Well, if this was a real process, we go, we've achieved nirvana. We've eliminated all our defects. Now, how did we do it? Well, come to find out, we figured out there was an electrostatic charge because of the low humidity, and for some reason, the defective red beads were repelled by that charge. So if I was really making white beads and this was a problem, I'd want to put a probe on the paddle, charge it up so that all the red beads were repelled. So I can learn from these trends. How do I improve my process? Now, the red beads actually is an example of a stable process, usually, that doesn't make its goal. I again invite you to view Dr. Deming doing the red bead experiment if you're interested in this process. It tells you a lot. So if my level is unacceptable, but I'm stable and predictable, which is the red bead experiment, I should color that as yellow and understand I don't need to figure out what changed, but I do need to figure out how to change the system that gives me that result. And if I am stable where I want to be, then I'm green. Don't mess with it. Now, as I improve other processes and systems, I may eventually in a few years go, well, that previously acceptable level isn't anymore. If you look at that OSHA case rate of about 15 years ago, we no longer consider a case rate above 1 to be acceptable. Fluor goals are much lower than that these days because we have improved our safety over the years and understood our trends. And P4, by the way, is the Professional Publications and Presentations program that us technical people get to record as we do presentations. And in fact, this presentation will be part of the Fluor P4 program. Now, we have something called the Global Information Management System, which is where we accumulate all of our worldwide safety data, which includes not only the lagging indicator of injuries, but also events such as equipment damage or motor vehicle incidents, and our observations that we do to try to prevent these sort of events. So it's a wonderful repository, and I do quite a bit of work in that for Fluor Government Group, my business line. And so charts are made that help us understand, for example, on the left-hand side, injuries of a certain type. We see it starts off with a red circle early in 2017. There was a spike, but then it kind of settled in. But then you'll notice from the chart, it's very visible that in May 2018, we started getting this increasing trend. We got the 7 in a row above average and actually shifted the prediction upwards to match the data. And we understood what was happening, and by the spring of 2019, we had counteracted it. You'll see it comes back down again, and we were actually at a lower baseline rate for this injury than we started with for what we learned. Another way to dissect the data, which has been very popular, is like, for example, compare body parts with injury types, because sometimes your top injury type may not be your top body part. That is, for example, and we see this in this chart, is one of the common examples is hand injuries tend to be lacerations, and back injuries tend to be sprains and strains. You don't tend to get lacerations to your back, and you don't tend to get strains to your hand. So you have to understand that difference, and that's what this right-hand chart helps you to see. And we also have accumulated these into scorecards. The left-hand side's an example of, I do like to put 4 charts on a page. And this is a while back at a project I support where, we do keep the traditional red, yellow, green stoplight. We turn it red if there's been a recent event. But more importantly, the upper right-hand chart talks about, well, what's my time interval between events? And then I also show for all the events, not only reportable but not reportable, where do they come from? And then I have my reportable and non-reportable events per month. And as we started this process, we noticed that it had been growing over the years. You don't even have to read the scales. You can see that if you see the control limits, see the lines, you can't draw any conclusion. But we've been going up in the middle third of the chart, and maybe we're tending down, but we haven't tripped a signal yet. Now I can accumulate all these reds, yellows, and greens by topic and by perhaps my business line. And this is an example too, where we were tracking corrective action management, which is some of the reds and yellows early on. How were we managing that? Did we self-identify things? And how did this break out by the different vice presidents and business lines? So it's a very visual way to take this technical statistical data and display it in a very action-oriented manner, so we can say, okay, these yellows are stable and predictable. I got to fix their systems. And these reds are something that the condition has changed. It's not like the others. I need to do something. Now, as we get through this, we also have to understand our data. And part of that is a little exercise, this is kind of in between these slides, a little exercise that works well with school children and also adults is get a box of animal crackers and ask a person, or persons better, to count the number of animals in the box. An interesting question. Now, first we have to realize there are no animals in the box. Those are crackers. But most people will say, yeah, there's 3 cows and 4 tigers, and yeah, show me that tiger. But even better is the idea of some of these crackers inevitably are going to be broken. So I have a cow head and a cow body. Is that 1 cracker or 2 crackers? So as I tell multiple people to take the same box of crackers, the same thing, and count the number of animals, I will get multiple different answers depending on how they counted it. In fact, Dr. Deming, who was a PhD physicist, said there is no true value of any measurement because it all depends on how you do the measurement. So now if we understand the context in which I got my data, and I understand when do I have a trend and one of these things is not like the other, I can tie that to risk management and say which of these things represents risk, especially in the case of the control limit in the bad direction. We've had great successes. So we have decreased defect, which has increased throughput in many places. I first started in maintenance world and at a project with a high corrective maintenance backlog, a lot of out of commission equipment. We understood our maintenance cycle times and discovered, there was backlogs in planning, getting the work package to the field was the problem. The field would execute the work pretty darn quickly, but getting the work to the field. And I've done this at a couple facilities now. And in another case, we discovered we had very specific planner types for scopes of work that we didn't have enough people to do the planning. Also, we found that we weren't ordering parts in a timely manner and perhaps getting the wrong parts. And also, were the procedures helpful? An interesting group came to me from Denver who's building light rail systems, trolleys in Denver, and they were having a little trouble with their grade crossing response times. You know, from the time the train is detected, how long does it take for the gate to come down? You don't want it to come down too soon because people will go, there's no train, I'm going to cut across it. And you don't obviously want it to come down too late or somebody be hit by the train. So we were able to understand what was the spread of times at certain crossings, and they weren't all the same, and we're able to tweak it in. And the Federal Railway Administration was very pleased with the results. They liked the formality of how we approached it. Of course, in several places we've understood, like the chart I showed of operational events, that also is a work stoppage. How do we reduce events? What is a common source of events, common causes? In one case I was at, a lot of it was we had some problems with our pre-job briefs and our preparations. So upon getting through that, a lot of our operational events went away. I've had the pleasure of doing some safety culture assessments and voluntary protection program. That's the OSHA VPP in the United States. They give a star status, which I've been very proud to be associated with several projects that have achieved VPP star. And for example, at one place we ran a personnel survey, and we found the one question that was the bell ringer question was senior management, that is above your manager, visits your workplace. And do you strongly agree, neutral, disagree, or strongly disagree? Now, that's a rather innocuous question, but we discovered that whenever that question was trending in the wrong direction, we went to some of the union stewards and safety professionals and said, something's going on, right? And they're like, well, funny you should ask. You won't believe that the following is occurring. So it really it didn't tell us, that question didn't tell us what was going on, but it said, go here and look. In terms of nuclear sites, we have lots of alarm systems. And in fact, there was a fairly significant event in the United States a few years back when an 82-year-old nun got into the Oak Ridge site. And they got all the way to the wall of a fairly secure building. And there was a lot of lessons in there in terms of false alarms and the alarm systems, which we considerably improved across the United States, and several facilities asked me for help in terms of let's understand our false alarm rates. Where are they? What causes them? And how do we eliminate them? And as I opened the topic with reducing injuries and illnesses. Now, again, context is important, so I want to talk about the people. And the introduction talked about Fluor's people, and I'm sure you are concerned for protecting your people. So this is all in context. I'm a big fan of Tom Peters, who said, hard is soft, soft is hard. As I alluded to with counting animal crackers, our numbers may not be as hard as we think they are. It all depends on how you collect the data and how you interpret it. In fact, I will say it's more important what you do with the data than what the data are. If you properly analyze your data, you will discover the flaws in your data and how to correct for them. So our actual numbers depend upon the method of measurement and can be pressure from expectations. If one's vice president said the next person involved in a first aid case is fired, you can bet there will be no reported first aid cases. And again, Dr. Deming said there's no true value of any measurement. So we do need to tie our statistical analysis and our understanding of is one of these things different than the other with the context of what's going on, as I spoke about mosquito bites versus rotator cuff injuries. Now, this is a fine flow chart, and I know it looks busy, but it's really what we've talked through today. I'll take you a quick run through it, but if you do look at the video recording of this or look at other presentations, perhaps that I or others have given, you'll discover the need for this thought. So we start in the center top with we gather data and we ask the question, is it stable and predictable or not? Now, if it's stable and predictable, we go to the left, and now we bring in our context. What is our benchmarks, our goals? What does our client expect of us? What do we expect of ourselves? We want everybody to go home safe, for example, and we don't want to make defects. And so we look at the stability and our expectations and say, am I okay? Well, if I'm okay, yes, don't mess with it. Just keep going around the cycle and monitor it and be sure that, the check engine light doesn't come on. This is like the check engine light on your car, by the way. Now, if we're not okay, if we're stable and predictable doing the wrong thing, we're injuring too many people, we make too many red beads, now's where I get my human performance friends and understand continuous improvement. I don't ask what happened last month. I say, what's been going on for years? What are we missing? What's the common causes to the failure to meet our goal? And most importantly, as the data screams out for action, we've got to hear the scream and say, what changes needed to the system and process and people to get this so I am stable and predictably making good product. So if I do make a change and I go back to the top, hopefully I'll go to that from SPC stable box and say, no, I'm no longer stable. I'm getting better. So I go over and say context and severity. Am I really getting better? And if like first aid cases went down, why did they go down? Did somebody say you'd be fired if any more were reported? Now, if it's down for the right reason, and this is a good thing, now we can reinforce and do lessons learned and color ourselves green, like that green yes. However, if my trend for some reason is going in the wrong direction, like in the safety topic where we had the equipment die and we had rotator cuff injuries, now we've got to look at what was the cause. The equipment died. And now how do we, in this new system, because I'm doing manual operations, how do I correct for the deficiencies of the equipment? How do I get an expert in like an ergonomist and fix it? And eventually that trend will end and I'll get an improving trend. So this is like the plan, do, study, act cycle, many improvement cycles, a little more detail and a tie to statistical trending. This is kind of the climax for this presentation. This is kind of the life, the universe, and everything wrapped up into one slide from my perspective and hopefully yours. So we've spent about a half an hour here, and I look forward to hearing your questions. I hope that you have questions, and we'll do a little more discussion. But the data can be, in Phil Monroe's words, can scream out for action. His friend Bill Cooper says, but somebody has to hear that cry, and we have to take action. So we can get fooled by randomness, which, by the way, is the name of a great book by Talem, Nalib Talem, I believe is his name. Just look up Fooled by Randomness. Really good book. Also, hey, watch the Powerball movie. Moneyball movie. There's lots of good documentation out there about understanding the difference between random noise and signal. And we need to understand the context. Can I count the animal crackers? What is it meant by an animal cracker? In fact, for my college classes face-to-face, I usually test the claim of Orville Redenbacher popcorn, my apologies there, for either popping less unpopped kernels or making more volume. And we actually will do a test to say, well, is that claim true or not? Let's test our claims. There's no knowledge without theory and testing that theory. So I've shared with you a statistical process control technique, well documented, but with the addition of the popular red, yellow, green overview for executive summaries. And it has worked and does provide a good improvement methodology. So I will close for the moment with, in God we trust, all others bring data.